right, so a proportion is no longer just a computation from a set of data. It is now a random variable of its own that has its own probability distribution. So just like last few chapters, we were looking at probability models and the mean and the standard deviation of a random event, and we didn't know exactly what that random event was going to be, but we could model it and we could calculate probabilities. That is now true for a sample proportion. It is now a random event on its own that we can model with data. We call this distribution the sampling distribution model for proportions. So you need to know what those words mean. When I say sampling distribution model for proportions, I'm talking about that histogram I showed y'all with the JMP software. I'm showing you sample proportions from sample to sample to sample to sample to sample, and I'm looking at that histogram. Even though we depend on sampling distribution models, we never actually get to see them. So that simulation that I showed you with the heads and tails, like we can simulate them, but most of the time we're actually just imagining them. I'm not even simulating them. I can only simulate certain ones that I can set up a simulation for. A lot of times I can't even do that. I have to just imagine what they look like. Remember, we have our conditions and we expect them to be normal, centered at P and all that kind of stuff, and that's what we imagine. Still, the sampling distribution models are important because they act as a bridge from the real world of the data to the imagined world of the statistic. So this is our bridge from basically from our sample to our population. These models are how we get there. That's our bridge. Real world, that's our sample. Population is our imagined world where we don't know. We don't study everyone in the population, so we don't have data from everyone. So that's why it's imagined. This we have data on. And they enable us to say something about the population when all we have is data from the real world or data from the sample, because our populations are often too big for us to collect data on. So, provided that the sample values are independent and the sample size is large enough, those are our two assumptions, which have three resulting conditions. The distribution of p hat, let's make sure we know what p hat is. P hat is a sample proportion. You are definitely going to need to be able to use the correct symbols here. The distribution of p hat is modeled with a normal model with a mean at p. P is the true proportion or the population proportion, which was in my simulation 50% for heads and tails. It was 20% when I did the other one with blue or not blue. And a standard deviation of PQ over N. And all of this is on your formula sheet on the bottom right side. All right, so let's take a look at an example. The centers, and I'm going to kind of write these symbols down as I read through the problem. The Centers for Disease Control and Prevention report that 22% of 18-year-old women in the United States have body mass index, BMI, of 24 or more. This is talking about all 18-year-old women in the United States. So this is a P, or a population proportion. So the first thing I'm going to do down here is write what P is. So P is going to be the proportion of 18-year-old women with BMI greater than or equal to 25. That's the contextual clues of what P is. That's what P is in this problem. Now, I know that that value is 0.22. Okay? 0.22. Now, let's keep reading. As a part of a routine health check at a large college, the physical education department usually requires students to come in to be measured and weighed. This year, the department decided to try out a self-report system. It asked 200, that's an N, randomly selected female students to report their heights and weights from which their BMIs were calculated. Only 31 of those students had BMIs greater than 25. Now that combined with N gives me my sample proportion, 31 over 200, which is a proportion of 0.155. Is this proportion of high BMI students unusually small? So in order to answer that question, I need to imagine what this histogram would look like. These from sample to sample to sample, what would we expect sample proportions out of 200 women to look like? In other words, where does this 0.155 fall in that histogram? Now, in order for me to even build that histogram, I need to make sure that I have an independent sample and the sample size is large enough. So I'm going to start with saying the sample is random because we need randomization, and we will assume 200 is less than 10% of all female students at this large college. We don't actually know how many female students are at this large college, but we would need this sample of 200 to be less than 10% of that, whatever that number is. So I am kind of making a little bit of an assumption there, but you do need to write it down and mention it so that you are telling the AP readers you know the conditions that need to be met. So I'll put a comma right there and say, so the sample should be independent. That's the first assumption that we need to make. The sample is independent. Next, we need the sample to be large enough. This is NP and NQ. So I'm going to come over here and find NP. Remember, P is 0.22. So 200 times 0.22 should be 44. And NQ, which would be 200 times the complement of 0.22, which is 0.78, is 156. Both of those numbers are greater than 10. So I'm going to add in here, we expect 44 to have BMI over 25 and 156 not to. Both greater than or equal to 10, so sample is large enough to use the normal model. All right, now that we know we can use the normal model, we need to find that normal model. So we're going to use normal model centered at P, 0.22, with a standard deviation of square root 0.22 times 0.78 over 200. So I'm going to go to my calculator and I'm going to type that standard deviation in. So this is the normal model that I'm using. Okay. I could draw that model out. I'm kind of running out of room here, but it's not, a bad idea to draw that model, 0.22, and then add and subtract off your 0.029s to get all of your standard deviations. But really what I want to do now is I want to compare the z-score, or I want to find where that 0.155 falls in this model. And I can do that with a z-score. So I'm going to take my sample proportion and I'm going to find its z-score. And I'm getting a z-score of negative 2.24, which means he's about out here somewhere. So this is where my p-hat is falling on my sample proportions. So that's more than 2 standard deviations below the mean, and that does seem to be a little unusual. So I would go ahead and say Only 31 out of 200 seems fairly low, as it is more than 2 standard deviations below the mean, which is unusual. Obviously, if it was even further away, it would be even more unusual, but this does seem to be on the lower side. So maybe the self-reporting system, people are not quite reporting their weight or their height or whatever properly, and maybe they're underestimating what their weight is, and so they're getting a lower BMI than what they really have, because we would expect 22%. So it's really important that you understand that you're comparing the sample proportion to the population proportion by its standard deviation. You have to know this number. You can't just say, oh, 15% is less than 22%. Remember, we expect sampling variability. It's how much different we quantify with our standard deviation. The standard deviation of the sampling distribution declines only with the square root of the sample size. Therefore, the variability decreases as the sample size increases. And a smaller standard deviation, the more accurate our results are. So that's a good thing. So we want to get bigger samples in order to reduce our standard deviation. That's a good thing. However, so there it's telling you we'd always like a larger sample, but the square root over that formula actually limits how small that standard deviation could be. So even if our sample size increased by 100, our standard deviation would only decrease by 10, by a factor of 10, because you got to take the square root of that. So square root of 100 is 10. That's an example of something called the law of diminishing return. So it doesn't actually benefit you to increase your sample size tremendously, because remember, that's going to be more expensive to do that. Be careful, now we have 2 distributions to deal with. The real world distribution of the sample, which we'd probably make a bar chart or a pie chart, and then the math imagined or sampling distribution of the statistic, which we model with a normal model based off the central limit theorem. Don't confuse the two. All right, and last, always remember that the statistic itself, p hat, is a random quantity. We can't know what our statistic will be because it comes from a random sample. Fortunately, for the proportion, the CLT, which is our abbreviations for central limit theorem, tells us we can model the sampling distribution directly with a normal model if the conditions are met. Please make sure you read through what can go wrong, what have we learned in AP Tips. Really good information in there. Chapter 17A.